Consider the following problem. One day, I'm very, very hungry, so I decide to order a pizza for lunch. I eat half the pizza, then I decide I'm still a little bit hungry, not quite as hungry as I was before though. So I take what's left, I cut it in half, and I eat that. I'm still hungry, but not quite as much as I even was that last time, so I'm going to take that remaining pizza, cut it in half again. If I were able to kind of keep doing this forever and cutting half of what's left and half of what's left and half of what's left and eating and half of what's left and half of what's left, at the very end, if I could keep going forever and ever, how much pizza would I have eaten? And the answer is if I could absolutely keep going forever, I would have eaten all of the pizza. So let's see if we can see how this would work mathematically. So before we begin, one of the issues with continuing forever is that we run up against infinity. And infinity is not a number, it's just the idea that we can kind of keep on going and keep on counting forever. So if we let something get infinitely big, our puny human brains do not actually like to think about that because everything that we've ever experienced before is finite. The number of grains of sand on a beach is a big number, but it's a finite number. The number of atoms in the visible universe, humongous, colossal number, but still theoretically a finite number because we can only see a finite number of planets. So while we can imagine infinity, we can't comprehend it very well. So one of the ways we can explore infinity is rather than using an infinite number, we just use a very, very large number and see what happens mathematically. So let's calculate the sum of the first 10. Let's think about the amount of pizza I'm eating as the terms of a sequence. So first I would eat half a pizza. Next I would eat a quarter pizza. After that I would eat 1/8 of a pizza. And we can see that this actually forms a geometric sequence. So let's let my T1 equal 1/2. We're going to let n equal 1,000,000 because that is a pretty nice big number. So if I could do that 1,000,000 times, I'm going to have some idea of about how much I will have eaten. Okay, so R, my common ratio, is equal to 1/2. So let's calculate Sn. So S sub n, sum of the first 1,000,000 terms of my sequence. I'm not going to write 1,000,000 because it just takes up too much room on my page, is going to be equal to T1, which is 1/2, times R to the n, so that's 1/2 to the power of 1,000,000, minus 1. That's all going to be over 1/2, that's our R, minus 1. And when I simplify this, if I do 1/2 to the power of 1,000,000, my calculator actually just doesn't handle it. It just tells me that's 0. It's not 0, but it's close enough for our purposes that it's basically 0. So we wind up with approximately a negative 1/2 over negative 1/2. In fact, you can see if your calculator is better than mine and try adding raising 1/2 to the power of 1,000,000. We've got negative 1/2 divided by negative 1/2, which equals 1. So this tells me mathematically that I have, at the end of the day, eaten one whole pizza. If I keep cutting it in half and eating half, cutting it in half and eating half of what's left, I will actually get through the whole pizza. Okay? So we notice that when n gets really big, r to the power of n gets closer and closer to 0. And if we could keep going forever, it would actually get there. We can't, but we can imagine we could. So what happens is when we have sequences where r to the power of n gets closer and closer to 0, the bigger n gets, we can count this Rn just as a 0. We can replace it with 0, and then we get a negative T1 over r to the n, r minus 1, and if we multiply numerator and denominator by negative 1, that gives us T1 over 1 minus r. So this gives us a much simpler formula. We don't call this Sn, we actually call this S infinity. So that's the infinite sum. If we could infinitely sum if we continued these sequences forever and we added up all the terms, we actually get a concrete answer for what that would reach. That's pretty incredible. Does this work with all sequences? Well, let's think about adding up all of our counting numbers. If we decided we were going to add up 1 plus 2 plus 3 plus 4 plus 5, etc., and keep doing that infinitely, you can see pretty clearly we wouldn't get to an answer because our number would just keep getting bigger and bigger and bigger each number we added on. So there's no infinite answer. We just get a number that just keeps increasing however many terms we add. So we have a word called convergent. So a convergent geometric sequence has a sequence of partial sums that approach a fixed value and terms that approach zero. So we have to be going down. It has to be a geometric sequence where my terms are getting closer and closer to zero. So for convergent, you think about raising to bigger and bigger powers. Convergent series, we know that raising fractions to bigger and bigger and bigger and bigger powers do get closer and closer to zero. Whereas once you get above 1, you're actually going to be getting bigger and bigger. Similarly with negative numbers, if you get below -1, you are going to be getting the absolute value of your number is going to be getting bigger and bigger and bigger and bigger. So convergent series our common ratio has to be between -1 and 1. And that actually includes 0 because 0 is, if you have 0 as your r, every term except the first one will be 0. A divergent geometric series has a sequence of partial sums that do not approach a fixed value. So terms that are not approaching 0, they may be getting bigger and bigger, or if you have a negative r, they may be flipping back and forth. So for divergent series, we know that r is greater than 1 or r is less than -1 if it's negative. So now let's take a look and see whether these series are convergent or divergent and state the sum. So the first thing we have to do, let's make this really clear, is our formula for S infinity only works for convergent series. If you try to plug values from a divergent series into the formula, you will get an answer. It's just not correct. So before we can even start using our formula, we need to determine if the sequence is convergent or divergent. And in order to do that, we need to find r. So this first sequence, r is equal to -1/3. Because -1/3 is between -1 and 1, our sequence is convergent. Now that we have a convergent sequence, we can go ahead and calculate our infinite sum. So S infinity is T1 over 1 minus R. Sorry, that 1 did not come through. Our first term is 1. 1 minus -1/3, which gives us 1 over 4/3, which is equal to 3/4. Okay, remember when you're doing 1 over something, you are taking the reciprocal of that thing. So let's look at B. Our common ratio of 2 minus 4 plus 8. So our common ratio here is -4 divided by 2 or -2. Okay, this sequence, -2 is smaller than -1. So this sequence is divergent. And we're done. We can't calculate S infinity because even though we'd get an answer, the formula doesn't apply to this type of sequence. It only applies to convergent sequences. So let's look here. We have 4, 8, 16. Our common ratio is 2. And this sequence is again divergent. Because it's divergent, S infinity does not exist. So let's actually write that in, that S infinity does not exist for letter B, and S infinity does not exist for letter C. So we can't calculate it, even though the formula would return some kind of answer. 1 plus 1, so D, we have 1 plus 1/5 plus 1 over 25. So our common ratio R is equal to 1/5. And because this is less than 1 and greater than -1, we have a convergent sequence. So we can actually calculate S infinity for this. So our infinite sum is going to be our first term, which is 1 over 1 minus r, our common ratio, which is 1/5. So this gives us 1 over 4/5, which is equal to 5 over 4. And so the idea is, and that's actually a pretty interesting thing, that if you take 1 and you add 1 plus 1/5 plus 1/25 plus 1 over 125, it's going on and on and on. If you're able to continue that infinitely, you would get to 5/4. And convergent and divergent sequences are not just geometric. And as you get into the study of calculus, usually in second semester calculus, you will start to look at some other sequences and series and then see if certain series are convergent or divergent. And there are some tests for determining whether they are.